All right. Hi, guys. Welcome to week five of our session today. So I'll be starting with the session first, and then Daniel will continue after half an hour or so. So I'll just share my screen. Can you guys see my screen? All right. Yeah. Is my screen clear to everybody? Good. All right. So we'll be starting out with this problem today on percentages, continuing where we left off last year or last week. So the problem says Gilda has a bag of marbles. She gives 20% of those marbles to her friend Pedro. Then Gilda gives 10% of what is left to another friend, Ebony. And then finally, Gilda gives 25% of what is now left in the bag to her brother Jimmy. So, what percent of her original bag of marbles does Gilda have left for herself? Right? So, in order to start this problem, does anyone have any ideas? Can you just any ideas on how we could start this problem? If not, I'll just continue. This one, the 2019 AMC problem. This one. My bad. I'll just clarify. Yeah, it's this problem. So the 2019 AMC problem. Right? Yeah, Gilda. So any ideas on how we could start? I'll just share what. So what I'd like to do in these types of problems is usually I just pick a number that works well with percents, and as you see that it makes it easier to visualize the problem as well. So um, yeah, you could definitely set a variable and do calculations like that. But I just like to, for me personally, if I was given this problem in the MCA, I'd just say, uh, Gilda has 100 marbles to start off with, because at the end it doesn't want a number of marbles, because if it wanted a specific number of marbles, then yeah, Gilda couldn't just start with any random number. But here it just wants the percentage. We'll get to that. So here at Gilda, it's the pound just asks for a percentage of marbles that Gilda has from what she had in the beginning. So I'll just say that Gilda has a random bag of 100 marbles, and as you'll see, saying that she has 100 marbles will make this problem a lot easier for us, because 100 is a very good number to work with when you're working with percents. So So Gilda has a bag of 100 marbles now, right? And she gives 20% of them to her friend Pedro. So how many does she have left? Remembering what we talked about last week. So if she gives away 20%, right? So as Suling said, yep, 4/5. So um, you 20% is 20 over 100, which is a fifth, right? So if she gives away a fifth, she has 4/5, right? So Gilda has 4/5 of 100. So Gilda has 80 marbles right now, right? Then Gilda gives away 10% of what is left to another friend, Ebony, right? So um, Ebony gets 10% of whatever is left. So what's 10%? So if Gilda gives away 10% of what's left, how much does Gilda have at the end? At the end of this process? So she starts out with 100. She gives away 20% to her friend Pedro, that means that she has 80 marbles right now because 20% is a fifth, and she gives away a fifth, so she has four fifths. And then whatever's left, the 80 marbles, Gilda will give away 10% of whatever's left to her friend Ebony, right? So if Gilda has 80 marbles right now and she gives away 10%, she has left 90%, right? So she gives away, so 10% is 10 over 100, which is a tenth, right? So yeah, 72. So if uh, if she gives away 1/10 of whatever she has, she'll have 9/10 left, right? So she'll have 9/10 of 80 left, which is going to be 72 marbles. And then finally, Gilda gives 25% of whatever's left in her bag to her brother Jimmy. So how many marbles does Gilda have at the end of this process? Yeah, so let's just work through it together. So 25% is gonna give you 25 over 100, which is a fourth, right? So Gilda is gonna have 72 times. So again, 72 times what, right? If she gives away 25%, that means she gives a fourth away. And so if she gives a fourth away of what she has, then she'll have three-fourths remaining, right? So she has 72 marbles, she gives away a fourth, so she has three-fourths remaining, right? Just simple fraction arithmetic. So she'll have three-fourths of 72 left, which is 54. So she has 54 marbles left at the end of all of this. And now the problem asks me, what percentage of her original bag of marbles does Gilda have left for herself? So her original bag contained 100 marbles. See, she has 54 left. So the percentage is going to be 54 over 100 times 100%, which is going to be 54%. So she has 54% of her original bag of marbles left with her. The answer is C. Like does this make sense to everybody? How instead of working through X and then saying um like 20% one fifth, and then you say, okay, so we'll just have like four-fifths of X left, and then doing those operations is obviously harder. But since we're working with percents, and the problem doesn't ask for a set number of marbles, you can this is usually a sign that you can work with any random number of marbles for Gilda. So if the problem doesn't ask for a set number of marbles, you can work with anything, right? So we'll just say Gilda has 100 marbles to start with. And obviously, as you saw in this problem, 100 is a very good number to work with if you're working with percents. So if you work with 100, usually everything works out, and they usually this process is way faster, and will usually give you accurate results if you work with it. So I highly recommend this method um, if you're working through this problem in the AMC or similar problems. Just setting a number. If it asks you for a percentage of something, right? Just set the number to 100 and then see how it works out. And so, without much calculation, we saw that the answer was 54%. So, yeah, I highly recommend this method. All right. So, now we're going to be talking about something new. We're going to be talking about proportions. It's not much different from ratios or percents. A proportion is usually just two ratios being set equal to each other. So, um, they usually take this form, right? So A over B equals C over D. So two numbers, you have the ratio of those two numbers, and then two bigger numbers or smaller numbers, and they also have a ratio. And so usually in proportions, this is what ends up happening, where K is some constant. So uh, what usually ends up happening is A over B is a certain ratio, and then C over D is the same ratio. And uh um so my bad. What I really meant here is I meant like C equals K times A and B equals K times D. And so what happens there is so what happens there is uh, basically if you have a ratio such as a over b, and you have another ratio which is c over d, but they're equal, the numbers usually vary by a constant k. And as you'll see, it won't end up mattering in the ratio, and they'll always be equal because a over b is always going to be equal to, so c equals k times a, and d equals k times b. So k always cancels out. And k can be k can be greater than or equal to 1, k can be less than or equal to 1 as well. So k can k can take any value possible, just the ratio always has to be the same. So you always have to have the same value of k above and below, right? So those are proportions. And then direct slash inverse proportions, this is kind of important. So um, usually a direct proportion is when you have a quantity x, right? You have a quantity x and you have a quantity y. And a direct proportion is usually if x increases, y increases. And if x decreases, y decreases as well, right? And so usually it comes in this form, x equals k times y. So k is a constant, again, similar to similar to this case. And so x equals k times y means that if you have a value of x and if you have a value of y, you increase y, right? Then x also has to increase to keep the same constant k. So let's say let's say you write k like that, right? So as you can see here, if y increases, right? If y increases, x also has to increase just to keep the same constant k, right? Because their ratio is always supposed to be x over y equals k. Does that make sense to everybody? So like say you have x over y equals k, right? And y suddenly becomes 2y. So x also has to become 2x just for the k to be just for k to be the same thing. So as x increases, y increases. And as x decreases, so if y became y over 2, x also has to become x over 2. And inverse proportions is when x increases but y decreases, or when x decreases and y increases. So an example of that is so x equals k times y. This is direct proportions. And inverse is when, say, x times y equals k. So I'll show you why this is the case. Because uh, x times y equals k will mean that as y, so say y became 2y, right? Now x has to become x over 2, right? Because x times y equals k. So if y became 2y and x also became 2y, k would become 4 times k, right? Because 2 times 2x times 2y. So that's 4xy. And so it's 4k. But if x decreased to x over 2, you have x over 2 times 2y equals k, because the 2 cancels out. So if you multiply, or if you increase y by a certain amount, say 2, 3, or some constant k, you have to decrease x by the same amount just to keep the proportions equal, or just to keep the product of x times y always equal to k. So this is usually the form that direct proportions type, or inverse proportions type. So just gonna know that this is inverse. All right, so with that knowledge, we can work through this first problem here. So it says Mike cycled 15 laps in 57 minutes. Assume he cycled at a constant speed throughout. Approximately how many laps did he complete in the first 27 minutes? So does anyone have any ideas on how we could start this? So just remember proportions and direct and inverse proportions. And so just like as we discussed here, when two ratios are set equal to each other, right? So Can two ratios be set equal to each other in this problem? Well, remember what we covered, or what Daniel covered in the first or second session about d equals v times t. So that's distance equals rate times time, right? And so speed rate, that's the same kind of quantities here. So speed equals distance over time, right? And so now do people see what we can set equal to each other, or how when proportions can be set equal to each other? Ratios, any ratios? Yeah. So what I underlined here, right? It says he cycled at a constant speed throughout. And a constant speed means the speed never changes. So the speed equals distance over time. So the ratio distance over time, so if speed never changes, this ratio also never changes, because speed is just distance equal distance over time. And so here, our distance is given in laps and our time is given in minutes. So as you can see here, the distance Mike cycles is 15 laps in 57 minutes, right? So this is his speed. This is his velocity. This is his rate, right? So 15 laps in 57 minutes. And this is the speed he's going throughout, right? And so it says approximately how many laps did he complete in the first 27 minutes. So if the speed never changes, what can we put as the ratio on the right side? So we can say that the number of laps Mike does in 27 minutes is x. So x laps in 27 minutes, right? Then we can say that he covers x laps in 27 minutes, because his speed always has to yeah, exactly, as Sulin said. So 15 laps in 57 minutes, that's this speed, right? And so he has to go the same speed for the first 27 minutes. So that means that he covers x laps in 27 minutes. And so setting these ratios equal and solving for x will give us equals 15 laps over 57 minutes times 27 minutes. And so this is going to be 19. It's going to be 9. And so it's going to be something like 135 over 19. And 135 over 19 is close to 7 laps. So 7, B. Yeah. Because as you see, 19 times 7 is going to give you 133. And so 135 is kind of close to that. So it's going to be approximately 7 laps at B. Yeah. For those of you who said B in the chat, yeah, you guys are right. All right. This is a bit more challenging. So it says that the ratio of W to X is 4 over 3. So by the way, is everyone fine with me writing proportions like this, or ratios like this as fractions? It just says that the ratio of W to X is 4 to 3, right? So W to X is 4 over 3. Yeah. All right. And then Y over Z is going to give me 3 over 2. And the ratio of Z over X is going to give me 1/6. Right. So what is the ratio of W to Y? All right. Can anyone give any ideas on how to start this? All right. So how about we start with dividing these? Oh my bad. Um, so how about we start with dividing these fractions, right? So w over x equals 4 thirds and y over z equals 3 halves. So if you divide those fractions, what do you get? Can someone tell me what you get? Both left and right side. So first thing we did was write ratios like this in fractional form, and then um, and then we'll just divide these two equations. And how do you know to divide? Because we have to find w to y, right? So if you divide w over x by y over z, right? If you divide w over x and y over z, you get some form of w over y, right? Does that make sense to everybody? Because I saw that w to x is 4 to 3, and y to z is 3 halves. And the ratio of z to x is 1/6. So what is the ratio of w to y? So I saw w and I saw y. So I'll just divide those, and I'll probably get a ratio of, because this is what we actually have to find. So w over y, this is the form of w over y. So I know that I have to divide those two equations. So if we do that, we get w over x times z over y. Remember, when you divide by a fraction, the fractions flip. So w over x times z over y, because y over c becomes z over y, right? Um, and on the right side, as someone mentioned, you get 4 thirds times 2 thirds, because again, 3 halves, the fraction flips, so you get 2 thirds. So w over x times z over y, oh my God, 8 ninths, right? Now, does anyone see how we can rewrite this left side to get our desirable result? Because we can rewrite it some way. So w over x times z over y. We are given some quantities and we're trying to find w over y, right? So we can rewrite it like this. So we can say w over y times z over x equals 8 ninths, right? That's how you can rewrite stuff. It's just something you can do in multiplication and division, and so you can always like switch and rewrite things. So as by the way, as long as they're on the um same side of the fractions, right? So you can switch w and z, you can switch x and y. Obviously you can't switch y and w, right? But as long as they're on the same side, as long as it's in the numerator or in the denominator, you can switch it. So um we're gonna get w over y times, we're given z over x as 1/6. So we're gonna get 1/6 equals 8 ninths. And so multiplying by 6 on both sides, right? We get w over x equals, so um we get w over x as 16 over 3. And so that, oh my bad, w over y, right? As I wrote here, w over y, and then w over y equals 16 thirds. And so our answer is E here. Did that make sense? So just to walk you guys through this. So first step I did was, it's kind of hard for me to visualize proportions just by looking at them as separated by semicolons, as you see here. So I'll just convert them to fractional form so that I can do algebra with it. So I have w over x equals 4 thirds and y over z equals 3 halves. Now, how do I know that I have to divide w over x by y over z? Well, because the question asks you to find w to y, right? And w to y is usually w over y, right? That's how you can write proportions in terms of fractions. So I'm gonna write w over x over y over z, and then the rest just follows through algebra and writing z over x as 1/6. That's just it. So does that make sense? So in an AMC, I'll always just recommend just writing your proportions, rewrite them as fractions, because then you can actually do algebra with it. Personally, for me, I can't really see or do algebra with proportions just by like the way they're written in terms of, yeah, in terms of Yeah, write it as an equation. Yeah, I just personally can't work with proportions, like with semicolons, right? So I just, I just recommend doing that. All right, all right, good. So we'll just do this last problem over here, and then we'll hand it over to Daniel. So, um, this last problem says that if the degree measures of the angles of a triangle are in the ratio 3 to 3 to 4, what is the degree measure of the largest angle of the triangle? Right. So uh, I have a triangle here, and some. So if it says that, actually we don't actually have to um declare, like, draw a triangle or do anything like that. So if the degree measures of the angles of a triangle are in the ratio this, right? So um what is the degree measure of the largest angle of the triangle? So now, since this is a proportion, right? um Obviously writing this as a fraction is difficult, right? Because there is three quantities involved, right? So what I just, because do you does so what's the sum of the angles of a triangle, first of all, just to start this question? What is the sum of the angles in a triangle, regular triangle? And it doesn't matter, but yeah, just a regular triangle, what's the sum? Yeah, 180 degrees, right? So 180. And so we know that the fraction always had the proportion, right? The proportion, um right now you can add 3, 3 and 4, right? And it'll give you 10. And we know that that's not equal to 180. Does that make sense? Because in a proportion, if you have some quantities x, y, and z, and it says, and so x, y, and z are your actual angles, right? So it's x, y, and z. And so x, y, and z are your actual angles. It says that x to y to z is 3 is to 3 is to 4. And then x plus y plus z equals 180, right? And so now, standing as it is, we see that x plus y plus z is definitely not 180. It's just 10, right? So what can we do? Well, going back to what I said about proportions here, I always said that you can always write a proportion as like k times a, as a constant, right? As a constant times the proportion. And if you multiply a proportion by a constant on each of the different components, so 3 to 3 to 4, if you multiply that by a constant k, um, well, the proportion doesn't change because you're essentially just multiplying or dividing by a constant. And so ultimately the ratio stays the same. So I can just say that the degree measures of the angles of a triangle are just 3x, 3x, and 4x. All I did was just take the actual proportion and then scale it by some amount x. And so if I scaled it by some amount x, it's still the same. It's like, um, I'll just give you guys an example, right? 1 is to 1 is to 2, right? And then 2 is to 2 is to 4. Are these the same proportions? Is 1 is to 1 is to 2 equal to 2 is to 2 is to 4? Yeah, right? They're the exact same proportion. It's just that I just multiplied that by 2. I just scaled 1 is to 1 is to 2 by an amount of 2, and I got this, right? So that's exactly what I'm trying to do here. So 3 to 3 to 4, I know that 3, 3, 4, all the different angles should add up to 180, and 3, 3, 4 obviously doesn't. So I'm just going to multiply that and scale that by a factor of x so that they do add up to 180. So if I add these and I get 180, I'll get the scale that I need to multiply 3, 3, and 4 by, such that I'll get that the angles are actually, like, the sum of the angles are actually equal to 180. So this will give me 10x equals 180, or x equals 18. So I know that I need to multiply 3, 3, 4 by 18, or I need to scale scale this ratio. I need to scale it by a factor of 18 so that these actually add up to 180. So now, if I scale it by 118, I get 3x, 3x, 4x. So this will give me 54 to 54 to 72. And now you can go ahead and verify if this actually adds up to 180. You can say that it's 54 plus 54, which is 108 plus 72, which is 180, right? So now it asks us for the degree measure of the largest angle of the triangle. And so what's the largest angle of the triangle? As you can spot very clearly here. Yeah, 72. And so the answer is D. So always always whenever the proportions don't match up to the actual sum, as we saw here, 3, 3, and 4, you can add it up and you can see that that's definitely not the sum of the angles of a triangle. You can always scale it up so that it does, or scale it down so that it does add up to the sum. And then you can just work things out and get the actual numbers, which both satisfy the ratio and also add up to 180 or whatever you want to add up to. And so with that, I'm going to transfer it over to Daniel. Yeah, thank you. Oh, you can hear me, right? I don't think we can hear you. Yeah, you're muted, or we just can't hear you. No, but no, we still can't hear you.
All right, I'm gonna use it without. Um, Kind of forgot how the microphone works. I haven't used it in a while. So, anyways, without further ado, I'm gonna screen share, and I'll just proceed without my microphone. All right, cool. All right, so hopefully everyone can see the screen. Thanks to Sid, who taught you about proportions and worked you through several examples from the AMC 10 and also 8 problems. Um, let's just start by recapping what direct and inverse proportions actually mean, because most likely you're going to see a couple problems that utilize the terms direct proportion and inverse proportion. So basically, direct proportion between x and y um, is such that we can represent x in terms of y with the equation x equals ky, where k is some constant. And then Sid wrote over here in this boxed equation, we can write k as x divided by y. We can also say like k is just the ratio of x to y, but we usually like to use the equation form, which is precisely by using the fraction x over y. Um, so the key thing about direct proportions is to notice that whenever we increase the value of a variable by some amount, the other variable will increase by that same amount. So if we increase, so what I mean by increase is by scaling. So when we scale a number, we multiply by that number by a certain constant. So if we multiply x by 2, right, we must have y double. So in other words, y also must be scaled up by 2. Um, the reason why I want to emphasize the word multiplies is that the ratio x over y is not equal to the ratio of x plus 1 uh, to y plus 1. So meaning that when we can't really increase one variable by a certain amount to guarantee that the other variable will also increase by that same amount. Does that make sense, Yabir? All right. So that's the key thing. We can multiply one variable by a constant and the other, and then that implies that the other variable will be multiplied by the same constant. We basically have a similar idea for inverse proportions. So if we increase one variable by a factor, let's say like if we multiply for sake of clarity a number by 2, then we must divide the other number by 2. So if we change x to if we double to x, right, we change x to 2x. But we can see that in order to preserve this relationship between x and y, we must divide y by 2. So y will become y over 2. There we go. And as you can see, we can just cancel out the constant that we just scaled it by to get x, y equals k, which is basically what we had at the start. So that's the basic idea of direct and inverse proportions. With direct proportions, when we scale up a number by some amount, we must scale up the other number by that same amount. And same thing with inverse, or a similar thing with inverse proportions. When we scale up one number by amount, we must scale down the other number by that same amount. So without further ado, let's try out a problem that utilizes direct and inverse proportions. So here, a variable x is directly proportional, we want to note this, to a variable y. When x is 3, y is 5. So what is the value of x when y equals 30? Right? So the way we want to think about this is that if we look back to our definition of or direct and inverse proportions, we know that if x is directly proportional to y, then we can represent x as basically a scalar multiple of y. So what that means is that we can write the ratio of x to y as a constant. So no matter what x and y will be, they must relate such that when x is divided by y, it's always going to be the same constant. This constant k will never change. So using that idea, we can actually just write the equation x to y, or x divided by y, equals a constant k. And so we can proceed by using the information about the values that they give us in the problem. So they give us the fact that when x is 3, y equals 5. So How are we going to use that to find the value of x when y equals 30? Well, remember the crucial fact that when two variables are directly proportional or even like inversely proportional, they're gonna divide or multiply to a same number. So in this case, because we're dealing with direct proportion, we must have a, a constant a constant quotient of x and y. So this k must be constant. So we can use that fact, um, as well as the values given here, to get our value of x when y equals 30. So let's just plug in the values that they give us, in one situation of this direct proportion. So in one situation, they say when x is 3, y equals 5. So we can just write 3 over 5 equals k. So now we can see that, um, we want to find the value of x in the second situation, which is when y equals 30. And of course, we want to find what x is. So in the second situation, we can write x, let's say this is what we're trying to find, divided by y, which is 30, right, in the second scenario, uh, equals k, right? It's just some constant k. But remember that these two k's are constant. So I'm going to write constant here, meaning that it never changes. So this can't be possibly be some another constant k2 where like k is not equal to k2, because we're given that x and y are in a direct proportion. So these two are the same constant. And then now it's easy to see that we can equate. We can just bring this equation over here, to get x divided by 30 equals k equals 3 over 5. And then note that k we don't even need to find k. Obviously, we know that k is 3 over 5th, which is 0.6, right? But remember that we want to solve for y. And what's really neat here is that, like, without even finding the value of k, you can find the value of x simply from knowing that x and y are in direct proportion. So we can actually just focus on these two values and equate them. And when we do so, we get x over 30 equals 3/5. Multiplying by 30 on both sides gives x equals 3/5 times 30. We can cancel one factor of 5 from the 30 and one factor of 5 from the denominator to get 15. Or sorry, this is 6. 18. Yeah, so 30 divided by 5 is 6. So we wanna write a 6 there. Yeah, sorry about that. So x is 18 when y equals 30. So that's one basic example. Now let's try this example on your own. It's a similar idea. I just changed the wording a little bit, as you'll see. So a variable x is inversely proportional to a variable y. When x is 3, y is 5. Again, what is the value of x when y is 30? So take a minute and think about that. And actually, I'll give you some a leading question. So um, what equation do we want to typically like write first as our just as a motivating step? Any ideas? Technically, there's no one equation, but typically I like to start with a more general one, just to like um, get a feel for what types of like relations I'm going to deal with the problem. Yeah, if not, that's fine. Um, so remember that I just changed the wording for this problem, but we can tackle this problem in a similar way from the previous problem. Let us write. Let us emphasize the word inversely proportional. So here, given that x and y are inversely proportional, It's just the same thing as saying x is inversely proportional to a variable y, right? So let's go back to what n what equation. So what equation uh, can can we use to relate x and y if they're inversely proportional? Is there any general equation we can use? Well, if we're relating this problem with the previous one, um, we can see that if x and y are directly proportional, we can write like the fraction. We can write the quotient between x and y as just a constant, so it just never changes. Um, Also, an important thing to note is that like there's nothing special about x and y in all these like relations, right? We can even write um, we can even write x, actually rather y over x is some constant k, um, because it really doesn't matter like what we're representing with these variables x and y. We can actually just switch them around and still get a constant, although the constant will be different, because if you take the reciprocal of both sides of this, like you'll get y over x equals 1 over k if we initially define k as x over y, right? But again, like 1 over k will never change, right? K is still a constant. So like motivated by writing this equation, we can do a similar process with inverse proportion. So with inverse proportion, right? If x and y are inversely proportional, they will multiply to one thing. Like just given that information, sometimes um, we have a third or even fourth variable that we want to relate, that may not result in x and y actually like multiplying to a constant. Like it could change depending on the values of the other variables. But in this case, in this problem that we're dealing with, x and we are only given that x and y are inversely proportional, so that we can just say that x times y equals k. So um, we can actually write the general equation x y equals k for some constant k. So again, we're going to use a similar process to how we dealt with direct proportion. So we're going to plug in for situation 1. So this time I'll write it out here. Number 1. Um, so in situation 1, we can write 3 times 5 equals k, which is plugging in x and y. And in situation 2, we want to find x when y equals 30. So this is situation 2. Oops, number 2. Um, so we're gonna do x, right? What we're finding times y equals k. Again, these two constants are equal, or because k just never changes in this situation. So we can just equate these two. X times 30 equals 3 times 15, which is 15. Dividing by 30 gives x equals 15 over 30, which is 1/2. And that's our answer. Okay, cool. We have one last example for direct and inverse proportion. So it reads, x is directly proportional to y, and y is inversely proportional to z. When x is 12, y is 3, and z is 2. What is the value of y when x is 72 and z is 6? Cool. I see a little different because we have three variables, right? We have x and y and z, and we want to relate them somehow such that we finally get the value of y, right? Um, and then note the general structure of these problems, of these direct and inverse proportion problems. We're given some general statement, um, such as like directly proportional or inversely proportional. Occasionally, I think you always see like joint proportional, but usually like you don't see that like too often. Um, but yeah, like that's like the first statement is usually just gives you some sort of relation with words, right? And then it gives you some sort of situation. This is like situation, as I called it in earlier problems. We can just call it situation number one. This is where like all of the values are given to you. So you know that when x is 12, y will be 3 and z is 2. And then it kind of follows it. Well, it doesn't necessarily follow from one value, but if you're given two, you can find a third one. Um, but actually for this first situation, um, this actually just gives you the constant that is relating situation one and situation two, right? This is the situation two is in the second sentence. This is situation two. Yeah. Um, so what I mean by situation one giving you actual values is that, like in this problem, you can actually find k, right? You can actually find what our product of x and y is in our inverse proportion. Because when we plug in, actually, when we start with a general expression, xy equals k, we can actually plug in the statement uh, from the second sentence to get our uh, value for k. So when x is 3, y equals 5, plug that in, you get k equals 15, right? And then similar to this, as I mentioned earlier, um, k equals 3/5, precisely because you can just plug in x and y, right, from the problem statement. So in a similar manner, right, how we have three variables here. So is there some way that we can relate all these um, quantities by multiplying or dividing or like even addition? But we usually don't use addition for proportions. So multiplying, dividing to get a constant, right? Because if we have a constant for situation one, we can equate a similar expression for situation two to find y. So does anyone have any ideas for what our constant might be? Our constant here is xy, right? And our constant here is x over y. If you just want to express the constant in terms of x and y. Yeah, so I'll just write k equals. So any ideas for what our constant expression might be? This is the key step of the problem because once you have that constant expression, you can just plug in for x, y, and z, and you can find y in situation two because you're already given x and z in situation two. So any ideas? Yes. Right. Because our call ends in 5 minutes. I'm just gonna I'll just demonstrate the key step in representing our constant in terms of x, y, and z. So um, x is proportional to y, and y is inversely proportional to z. So thinking of if I can do it in two equations. So the constant that pops out to me, which like might seem arbitrary at first, is k equals x over y z. And like inspecting this equation, we can see we expect inspecting this constant. I mean, we can see how all of these conditions are satisfied, right? So x is proportional to y. So what does that mean? If you increase x, if you yeah, what I mean by increase again is by multiplying or dividing by like a constant, right? So if you increase x by some amount, you must uh, decrease y by the same amount. So x increases, y increases. So the numerator will be scaled up. The denominator, however, will also be scaled up. So first condition, x is proportionally um, proportional to y is satisfied. Now y is inversely proportional to z. So what does that mean, right? YZ is a constant. Y and z multiply to one constant. Um, so let's keep x fixed, right? What happens if you increase y? Well, um, well, to preserve that constant, right? If you increase y, and again, we're gonna let x be the same. So assuming that x is the same, if we increase y by something, we must decrease z by that same something. Because if we don't, right? If you just leave z as it is, the net change in this expression is that the denominator is going to be increased and k will decrease as a result. We don't want that, right? And if you increase z, right, again, this leads to the same result because the denominator is increased, k will decrease, so we don't want that. Again, k should be constant. We want to equate a constant so that we can find x, y, and z. So this is why we can just have yz as a scalar. So like when y is increased, z must decrease. So this is our constant. Um, so um, we're gonna plug in for situation one, which gives us k equals x, which is 12, y, which is 3, and z, which is 2. And then equate that with situation two. So which is x is 72, y is something, and which is whatever we want to find, and z is 6. So this will turn out to be 2 equals 12 over y, and y equals 6. That gives it our answer. Okay, so that is all. Thank you everyone for attending. Hope you learned something new about proportions. And next week we'll
Yep.
be covering unit conversions and algebraic manipulation. So see you
All right.
all next
Thank you,
week.
everybody. Yep. See you next week. Bye.